So for these problems where we're asked to find the linear approximation of a function, we have to remember that the linear approximation function, and that's the L of xy, that's just equal to the tangent plane, which we would call z, okay? So that means that our first step is to go ahead and find the tangent plane. Now I know in the last problem I did a special case where we had a tangent plane that was parallel to the z-axis, and that made it so that z was not part of our tangent plane. That is not true for this one. In this one, we have to notice that when an equation f of xy is equal to 1 minus xy cosine of pi y, we would replace the f of xy with z. Okay, so z is involved in this equation. It's z equals 1 minus xy cosine of pi y. And so this is not parallel to anything. And that means that when we want to find our tangent plane, we're going to be finding the equation z equals f sub x of ab times x minus a plus f sub y of ab times y minus b, and then plus f of a b. Okay, that's our tangent plane, and it's also our linear approximation function. So in order to come up with this, we need to find all the parts. We need to find our partial derivatives. We need to know what a and b are and what f of a, b is. And so we have a little bit of work to do. I'm going to find f of a, b first. F of AB, well, A and B are 1 and 1, we're told, because they tell us to find the linear approximation at 1, 1. So I'm going to go ahead and plug 1 and 1 into my function. I get 1 minus 1 times cosine of pi. This gives me 1 minus a negative 1, or 2. All right. The next thing I can find are my partial derivatives. So I know my function up above is 1 minus xy cosine of pi y. So f sub x is going to equal del x of 1 minus xy cosine of pi y. Now notice if we take the derivative of 1, we just get 0. And then in the next term, I have x times 2 functions of y. Well, the functions of y are just constants. So when I take the derivative of x, I just get 1 times the constant, so I get minus y cosine of pi y. And I can drop the 0 and just write this as minus y cosine of pi y. Now I need to know what my partial derivative with respect to x is at the point 1, 1. So I plug in 1 and 1, I get negative 1 times cosine of pi, which is going to give me negative 1 times negative 1, or positive 1. Okay, I have 2 of my parts. One more part, I need my partial derivative with respect to y. So this means I'm finding del y of my function 1 minus xy cosine of pi y. Now there's a product rule here because I do have 2 functions of y in one of my terms. But the derivative of 1 is 0. And then I'll rewrite this as minus x, since x is a constant, I'm going to pull it out, times the derivative del y of y cosine of pi y. So now I can really focus on those functions of y, and the x isn't in my way. So this is equal to negative x times, and I'm going to do my product rule, del y of y times cosine of pi y plus y times del y of cosine of pi y. All right, now we can go ahead and take the derivatives. Derivative of y with respect to y is 1. So my first term simplifies to just be cosine of pi y. Then I get plus y. The derivative of cosine is negative sine of pi y times, and now I'm going to have the chain rule. I need del y of pi y. Okay, so a couple more steps here. We're just going to get this is equal to minus x times cosine of pi y. And then I have minus, now the derivative of pi y with respect to y is just pi. So I get minus pi y sine of pi y. Okay, now I don't need to distribute. I don't need to simplify this anymore because I just need to know what my partial derivative with respect to y is when I evaluate it at 1, 1. So on the outside, I get a negative 1 times cosine of pi minus pi sine of pi. Sine of pi is 0. Cosine of pi is negative 1. So I get negative 1 times negative 1 is 1. Okay, I have all my pieces. I have f sub y is 1, f sub x is 1, f of ab is 2. I'm going to plug those all into the equation at the top of the screen for the equation of my tangent plane. So the plane, goodness gracious. Okay, so the plane is, I should specify, the tangent plane is z equals 1 times x minus 1 plus 1 times y minus 1 plus 2. And this simplifies to be z equals x plus y minus 1 plus 2. Those all go away. So it's just z equals x plus y. Okay, this is the tangent plane. The second step says, remember the linear approximation. Is equal to the tangent plane. Since I found my tangent plane, I can go ahead and rename it to be L of xy is equal to x plus y. Okay, so I found my linear approximation function, and now I'm going to use it. Use to approximate, and let's see, what were we approximating? F of 1.02 with 0.97. Okay, so here's what that means. It means that we're going to, when we go to evaluate our function f of 1 at 1.02 with 0.97, instead we're going to say, you know what, well, this is just approximately the linear approximation evaluated at 1.02 with 0.97. And that, I can just plug in these values to x plus y. I get 1.02 plus 0.97 for a grand total of 1.99. That is the value on the tangent plane when I plug in those points. It's not actually the value on the surface, but it's a good approximation. So last thing I could do is to compare with exact. And that means I would actually plug in 1.02 and 0.97 into 1 minus xy cosine of pi y. I should plug in the numbers. 1 minus 1.02 times 0.97 times cosine of 0.97 pi. And when I plug that into my calculator, I get that this is approximately 1.985009008. And so that's pretty close to what we got in the approximation with the linear approximation. To the hundredths place, we've got some pretty good accuracy. That may or may not be good enough, just depends on what you're working with. Okay, so those are tangent planes and linear approximations. The takeaway from that is that when you are asked to calculate a linear approximation, it is the same as being asked for the equation of the tangent plane, and then you will just rename it L of xy, and then you will use it to make an approximation. That's it. All right, the next topic is the differentials. So way back in Calculus 1, we learned how to take the derivative of a function, y equals f of x. And what we learned from, working with y equals f of x is we would say, oh, okay, well, dy dx is equal to f prime of x. Now, if we were to separate that fraction dy dx by multiplying both sides by a dx, this would become dy is equal to f prime of x dx. And what this is known as is the differential. And we worked with the differential a bit in Calculus 1. We may or may not remember that, but we are going to work with it again in Calculus 2. And now I want to talk about it different than the way that it's referred to in Calculus 1, because this little d is actually an operator. So d equals a derivative operator. And it takes derivatives with respect to any variable. And so it'll handle product rules, chain rules, all the stuff, all the things, quotient rules. But what it's doing is it is giving us an incremental measurement. So when, below here I have dz. Let's see, we start with, we've got z equals f of xy. And then I'm telling you that the differential dz is equal to a partial derivative with respect to x times dx plus a partial derivative with respect to y times dy. And that is true. But the differential dz, it's basically telling us an amount of change, the amount of change that occurs in a tangent plane when there is change in the x and the y values. That's what dx and dy are representing. And so technically, if we and I'll show you in an example where we're working with the differential operator and what we do with it. But basically, the little d comes through and it's like, hey, I'm going to take little d of z equals f of xy. And it's like, okay, little d, I'm going to say, okay, d of z. Okay. And then it's going to say d of f of xy. And when d acts on z, it's like, hey, you're just a variable. You're just z. Derivative of u is 1, right? But with respect to what variable did little d just take a derivative of? Oh, well, that was z. So we're going to put on a dz. Then I go to the other side of the equal sign, and little d is going to act upon our function f. And it's like, hey, I'm little d. I want to take a derivative of you, big F of xy. Oh, wait, you have two variables. I'm going to have to deal with you carefully. And so it's going to run through, and it's going to be like, all right, first, I want to deal with the x's. So I need to take derivatives with respect to x. And so I get f sub x, but I put those all together, and I've got a dx. And so it kind of like lets us know that, the function that's next to dx is a first partial with respect to x. So then little d is like, wait, there's one more variable. Let me hit the other variable. I'm going to go ahead and add in the partial derivative with respect to y, but we need a way to know that it's the partial derivative with respect to y. So we've got a dy that shows up there. And so that's what we're seeing up above here. Now, visually, what's going on here is we're just measuring change. If we think back to Calculus 1, like in this first picture here, in Calculus 1, when we worked with this, we're examining what happens if I take a step from x equals a to x equals a plus delta x. There's going to be some change in x, right? It's dx or delta x. They mean the same thing. But when we change an x value, there's going to be a corresponding change in the function value, as well as a corresponding change in the equation of the tangent line value. So delta y is the change in the value of f of xy, whereas dy was the change in the value of the tangent line. So a little bit different, right? And now we step away from the two variable system and we go to a three variable system, and suddenly this picture just gets a little bit overwhelming. So we're working with 2 points here. We've got a point on this upper left corner, and we're going to go to this point in the upper right corner. The blue is the surface, and it's named surface is z equals f of xy. And the yellow underneath it, that's the tangent plane. So fortunately, everything's pretty labeled. Now, if we're starting at a point A, B with f of a, b, and we make a small change in x and we make a small change in y, those small changes are going to be named delta x or dx and then delta y or dy, okay? And those mean the same thing. So we're going to change the x value, change the y value. When we do that, where is the new z value? And that's up here in this upper right corner for the surface, and it's right here in the upper right corner for the tangent plane. So at the first point, the AB with f of AB, that was the same point for the surface as it was for the tangent plane. Little change in x, a little change in y. We end up with two unique values of z, one for the tangent plane and one for the surface. Now, the change that occurs in the z values for the surface, that is the delta z. So this is the change in the z values of the surface. Whereas dz is the change in the z values of the tangent plane. Okay? All right, so now that we've seen all those pictures and everything, we're going to apply this to some application problems. So in this particular problem, we are working with the differentials, and we're going to be using them to measure error. And in this particular one, we have a circular spot 7 feet in diameter, and it's 3 feet deep. And we're going to use the volume formula, pi r squared h, to find the volume of the pool. And then so we'll do those things first. Then, if the measurements are accurate to within 0.05 feet, then use differentials to estimate the maximum error in calculating the volume of the spa. And then also calculate the exact error in volume, delta V, and compare the two. Okay, let's start with a picture. So I'm going to draw a spa, which basically is just a cylinder. And I'm going to put this on an axis where the diameter can run along the y-axis and the height can run along the z-axis. So along the y-axis, we go out to 7, and along the z-axis, we go up to 3. So it's representing diameter and height. I am going to name diameter y. Height will be h. And there's a reason why I'm choosing y. I don't want to use d because I'm going to be taking little d of things, and I don't like to have two little d's in places. It's just confusing. Okay, so if I use those variables for diameter and height, then the volume is equal to pi r squared h. Oh, wait a second. I have r in there. R is radius. Radius is half of a diameter. Okay, so I'm going to replace r with y over 2. Okay, so now I've got my volume in terms of the y's and the h's. Let's just simplify this a little bit. V is equal to pi over 4 y squared h. Okay, now let's see, what else were we asked to find? Find the volume of the pool. Okay, using the measurements that they use, 7 feet and 3 feet, let's figure this out. So the volume is equal to pi over 4 times the diameter squared, so 7 squared, times the height, which is 3. When I plug this into my calculator and get myself to the hundredths place. It's about 115.45 cubic feet of volume using those measurements. Okay, now when they tell us that the measurements are accurate to within 0.05 feet, so this whole statement just means that dy, so the measurement in the error in the measurement of diameter is equal to 0.05 feet, and the error in the measurement dh of the height is equal to 0.05 feet. So there's this possibility that there's accuracy only to 0.05 feet. Okay, these are the errors. And I think that that might be one of the harder parts about these problems, is understanding that these, before it was just a differential, and now it actually has a meaning. So dy's, dh's, dz's, they all are measuring error in this problem. Okay, so now we've gotten through that third sentence. We want to use the differentials to estimate the maximum error in calculating the volume of the spa. Okay, so dV equals the maximum error in calculating the volume. So that means we need to come up with a function for dV. So we're going to take little d of v equals pi over 4 y squared h. Okay. Little d is going to run through, and it's going to take derivatives. So we get d of v equals, and now I've got pi over 4, so I can pull that out. And inside now I have d of y squared h. I'll just put parentheses there. Okay. So when little d comes across v, it's like, hey, you're a variable. You're just the v. I'm going to take the derivative of you, and your derivative is 1. Okay? Times a dv, right? Because we need to know what variable we're differentiating with respect to. This is equal to pi over 4. Okay? Now, I'm going to go ahead and open this up. Now what I want to do is I need to take, well, I'm taking little d and there's a product, so it looks like I need a product rule. Okay, so I'm going to take little d of the first, so little d of y squared times the second, h, plus y squared times little d of h. Okay, let's very carefully clean this up. On the left, we'll simplify that to just be dv. On the right, we have our pi fourths still hanging out. All right, little d of y squared. I'm going to take the derivative of y squared. It's 2y. But little d is like, hey, we need a dy in there so that we know what the derivative was with respect to. And then this is times h plus y squared. Okay, now little d is going to act upon h. When little d takes a derivative of h, a linear term, the derivative is 1. But we need that dh in there in order to know what variable was being dealt with there. All right, one more step to clean up. We have dv is equal to pi over 4 times 2hy dy plus y squared dh. Okay. Now, what I want us to do really quick is just look at v equals pi over 4 y squared h, and just really quick calculate, what is v sub y? Well, v sub y, we would pull the pi fourths out to the outside, and it would be 2y h, right? That's what we have right here. You know, the h and the y are switched, but that is our first partial with respect to y. And if I was to calculate v sub h, the first partial with respect to h, there's just an h in there. The derivative of it is 1, so I'm just left with the pi over 4 y squared, which is what I have right here. Okay, so I used a different method where I didn't actually memorize a format. I just used the operator like I know how to with derivative operators. It just takes some getting used to because it's a little d and it's not d dx, it's not del del x, it's just d. So that's kind of strange. Anyways, now what were we doing? So we found a function for our max error. Now we actually need to figure out what that maximum error is, okay? So the max error, I'm still using blue here, our max error, and you know, I should actually do a little, it's actually approximately dv, and that is going to equal pi over 4, and now I have to replace everything in here. I have a 2. Y is the diameter that was measured, so that's 7. And the h, that's our height, that's 3. And dy, well, we were told up above it's 0.05. Okay, plus y squared, that's my diameter squared, 7 squared. dh is 0.05. Okay, plug that into your calculator, get an answer. I got, this is about 3.57356 cubic feet. Okay, so this was an approximation of the maximum error. And the reason why it's an approximation is because we use the equation of the tangent plane there, in a sense. dz is giving us a measurement on the tangent plane, like what happens if we change those values 7 and 3 by 0.05, right? So this value that we found here is actually a value that is on the tangent plane, not on the surface, that is our volume, okay? So the exact error is the next thing that they're asking us to calculate. So calculate the exact error in volume, delta V, and compare the two. Okay, so exact error is delta V, and that is going to be V evaluated at 7.05 with 3.05. And those values I chose because they are 0.05 or, you know, a DH or a DY value away, minus V of 7.3. Okay, so this is going to equal pi fourths y squared, so 7.05 all squared times 3.05. That's the volume at 7.05 and 3.05, minus V of 7.3, we already found that, but I'll just write it out again, pi fourths times 7 squared times 3. All right, when I plug this into my calculator, I get approximately 3.60703,924 cubic feet. Okay, so we can see here very clearly that dV does not equal delta V, right? But it is a good approximation of the error. Okay, now I wouldn't say it's fantastic, but it's pretty good. You know, if we were to round the dV value to the nearest tenth place, it would be the same as the exact error. So it's good to the tenth place, right? Okay, next problem. If R is the total resistance of 3 resistors connected in parallel with resistances R1, R2, and R3, then we get this equation here, and this is Ohm's law. And it says 1 over the resistance, total resistance, will equal the sum of the 1 over each of the individual resistors, okay? And then it says if the resistances are measured in ohms, and it gives us values for R1, R2, and R3, with a possible error of 0.5% in each case, estimate the maximum error in the calculated value of R. Okay, first things first, the max error is approximately D big R. Okay, in order to get D big R, now I'm going to go by the formula that we were given earlier. So D big R should be equal to the partial derivative of R with respect to R1 times dR1 plus the partial derivative of R with respect to R2 times dR2 plus the partial derivative of R with respect to R3 times dR3. So it is the sum of the first three partials, each getting multiplied by their own individual differential. Okay, so that's what we're going to have to calculate, but we have to come up with all the pieces. So first, I want to deal with this possible error of 0.5% in each case. So they're talking about the error in measuring the individual resistors. And so what that means is that so possible error is D's. So we're looking at dR1. The possible error is 0.5% of the actual measured value of R1. And so we would write that as 0.05 times, 0.005 times the actual R1, the 25. And we multiply those out and it gives us 0.125 for a value of dR1. dR2 has the same possible error of 0.5%. That's of the measured value of R2. So this would be 0.005 times R2 is 40 ohms. And so this gives us, when we multiply it out, 0.2. dR3 is going to be 0.5% of R3. And we write that out as 0.005 times the R3 measurement was 50. And we work that out to be 0.25. Okay, so I have my differentials. Now I need my first partial derivatives. So del R, del R1, del R, del R2, del R, del R3. Looks painful, but I think we can do it. So let's first deal with del R, del R1. That means that we're going to take del R1 of both sides of the equation up above. So of the 1 over R, and then del R1 of 1 over R1 plus 1 over R2 plus 1 over R3. Okay. Now we have to take these derivatives knowing that we're actually dealing with an implicit function because we don't have R solve for. We have 1 over R. And so when I take the derivative of 1 over R, I do so remembering that big R is a function of R1. So I'll take the derivative of 1 over R and get negative 1 over R squared. Put that square in the right place. Times, and the chain rule says times del R1. Okay. On the right-hand side, I'm going to send the del R1 through. When it hits the 1 over R1, I get negative 1 over R1 squared. When it hits the 1 over R2, that's a constant. And so is 1 over R3. So those are all 0. That means now I can solve for del R1 by multiplying both sides by negative R squared. And I get positive R squared over R1 squared. Okay, that's cool. That's a lot nicer than I thought it would be. So then we look at del R2. So we're doing the same thing. We're taking del R2 of 1 over R. It's equal to del R2 of 1 over R1 plus 1 over R2 plus 1 over R3. Okay, on the left, same as before. I have to implicitly differentiate 1 over R. So I get negative 1 over R squared times del R1. Nope, del R2. On the right-hand side, I send the del R2 through. In the first term, 1 over R1 is a constant. The second term, 1 over R2, is going to give me minus 1 over R2 squared, and then plus 0. Okay, so again, I need to solve for del R2 now. And I do so by multiplying both sides by negative R squared, and I get a positive R squared over R2 squared. I'm hoping you're seeing the pattern and that you can accept that del R of del R3 is going to equal R squared over R3 squared. I'm going to put a similarly up here. If you don't believe me, work it out. You'll see it. Okay, so I have the pieces of the first partials. Now, there's a lot of work. Now what I need is to actually plug in those values. Okay, so I was given R1, R2, and R3. I was not given R. Okay, I need to evaluate the first partials at R1 equals 25, R2 equals 40, R3 equals 50, and R equals question mark. So we need to find R. We don't know what it is, but we have a function. We know that 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Definitely know that. So we plug in those values. That's it. So 1 over R will equal 1 over 25 plus 1 over 40 plus 1 over 50. And when we do the math, this all works out to be R is equal to 200 over 17. Okay? All right, now we have everything we need. We can plug it all in. We can calculate dr. dr, so this is our max error, is approximately dr, which is equal to del R1, right? We need that. Maybe we should write this out first. Okay, so we're going to do R squared over R1 squared dr1 plus R squared over R2 squared dr2 plus R squared over R3 squared dr3. Okay, and now I can plug it all in here. Okay, this is equal to, all right, I've got, oh, look at that, I have an R squared in common in every single term. I'm going to factor that out. That's 200 over 17, all squared. Inside, I have my dr1, that's 0.125 over R1 squared. R1 is 25. Okay, my second term, remember I factored out an R squared. So I just have the dr2, which is 0.2 over R2 squared. R2 is 40. Plus the dr3, 0.25 over R3 is 50, so 50 squared. Okay. Funny enough, when you do all the math on this, if you do it by hand, this cracked me up. This is actually equal to 1 over 17. It actually comes out to a nice fraction. But for those of you who love decimals, this is 0.058823529. That's what my calculator would give me. 1/17th is actually the exact value of the approximation of the maximum error on the measurements of the resistances. So that's it for this section, 14.4. We covered the tangent planes. We saw how the linear approximation function is the tangent plane, just given a new name and used to make an approximation. Then we learned about the differential, which is also used for finding some approximations of errors and such. So if you have any questions at all as you're doing your homework, please reach out.